Welcome back for the second of our four-part series on glycolysis. In this one, we are going to look at each of the 10 steps in glycolysis. Last time we looked at an overview, and so now we're going to look at each of those reactions. So as a reminder, glycolysis is a small piece of our metabolism, but a very important one. And if we look at this a little closer, here's our glucose. So we're starting glycolysis with glucose. And we consider the end of this glycolysis piece at the pyruvate. And if we look here, you'll notice we make this glucose 6-phosphate on the way. So we're moving our way. There's 10 steps to get down to pyruvate. And we looked a little bit at this glucose 6-phosphate last time. So if we look at step 1, we know that our enzyme is a hexokinase. And if we remember kinase, we're talking about transferring a phosphorus from ATP to another molecule. And then the hexokinase tells us it's from this 6-member carbon ring. Okay, so if we look, I have a phosphorus here, or a phosphate, that ends up over here. So remember, ATP is shorthand. And this is a whole phosphate on that ATP that ends up. And if you remember, we talked about this one last time, and we talked about the fact that that phosphate is really important because glucose gets ported into the cell, and then it gets this phosphate added. And when it gets that phosphate added, that transporter can no longer recognize this, and it gets stuck in the cell. So that's one reason that that phosphate is really important. Okay, so that is the first step. The second step, let's look at our, at our term for our catalyst, okay, our enzyme. So phosphoglucose, so there's our starting molecule, right, over here on the left. Phosphoglucose isomerase. So think what isomerase sounds like. We're going to rearrange. So let's look at this because it seems like we're looking at 3 reactions. When we look, this first part, remember that we have an equilibrium between our closed, our cyclic molecule right here and our open chain version. Okay, that equilibrium tends toward the cyclic, but we do have the open chain version. And when we have that open chain form, this catalyst can act on this open chain form. And look what it does. It moves this carbonyl from the first carbon to the second carbon. Okay, so it moved it down a carbon. So now we also have an equilibrium between the open chain and the ring structure. But now, when this oxygen comes around and attacks that carbonyl carbon, we're going to get a 5-member ring. Okay, we're going to get that fructose ring. So now it's fructose 6-phosphate. All right, so that was our isomerase. You don't need to memorize these specific names, but you do need to be able to think about what they're doing and know the general ideas of what's happening in each step. So if I gave you a list of, say, catalyst enzyme names, and I was like, oh, which one would do this? Well, you'd be like, oh, that'd be the isomerase, right? Because we see we're moving, we're shifting things around. All right, keep going. So step 3. So in this step, first thing I want you to look at these arrows. That forward arrow is dramatically longer than the reverse. That is telling us something, that the driving force for this reaction is in that forward direction, okay? And really, we consider this reaction largely irreversible. It's catalyzed by this phosphofructokinase. So lots of words, right? But phospho, so we have a phosphorus. Right? Fructo, we've got that fructose cyclic compound. Kinase, we expect to see ATP and a phosphorus transferred. Okay, so phosphofructokinase. And we're starting over here. We have right here, this piece is going to gain that phosphorus. This is an important regulatory enzyme. In fact, this is the main regulatory enzyme. It's allosterically controlled, and this is kind of the regulation piece of our glycolysis step. Do you remember the term high phosphoryl transfer potential? We looked at that in the last, or maybe it was, anyway, we have looked at that in a previous video. And remember, ATP has a high phosphoryl transfer potential, right? It has a driving force to give away that phosphorus. All right, step 4, this aldolase is our enzyme. And let's look at what's happening. We have this reversible process where we are breaking our molecule down into 2 small 3-carbon molecules. Okay? This can go in either direction. It'll be driven in one way or the other depending on the substrate conditions and the cellular conditions. But remember that this is a full 10 reaction cycle. So this molecule right here is actually going to get used up as we move on. And so that will, think Le Chatelier's principle, that will drag this whole reaction forward. All right, onward, step 5. Look, we have a nice isomerase again, right? So if I think of isomerase, I said, I think I'm moving something. This time we were starting with that triose phosphate. So we have our 3-carbon molecule with a phosphate. And look at what's moving. We're moving that carbonyl from the middle carbon to the end carbon, okay? And it's happening because that form is needed for the next reaction. And at this point, let's draw a little squiggle here. We're at the end of the phase where we are using energy to drive this, and we're about to enter the energy generation phase. And it is going to start with this molecule. Okay, so we have, hold on, let's go back up here real quick. Notice we have 2 different molecules, DHAP and GAP, but GAP is the one we really need as we move into the energy generation phase. And so step 5 is taking that other product and converting it. So at the end of step 5, we have 2 of these molecules right here. Okay, and now in step 6, we're going to start reacting those molecules. Okay, so we have that here. And remember, really, this reaction will happen twice because we have 2 of these molecules. But we're just going to look at it for a single reaction. So let's take a look at our naming here. So we have dehydrogenase. When you see that, I want you to start thinking about a redox reaction. Okay, so we're going to think of a redox reaction. And if I look, I can see that that carbon is being oxidized, right? We see that extra bond now to an oxygen. So one thing that's happening here is that carbon is being oxidized. And that is going to give off some energy. If that's oxidized, something has to be reduced, and our NAD plus gains a hydride ion. So this is weird, right? It's got a negative charge, which if you think about it, means it has 2 electrons. So that NAD is now NADH. Okay, that takes energy, but that's going to be useful to us later. It's essentially carrying these 2 electrons down to our electron transport chain. And overall, that oxidation has given off enough energy all right, to provide the energy to add that phosphate that goes right there. Now the next slide is this same reaction, but let's think of it in 2 steps. Okay, so in the top part, we oxidize that carbon. Okay, that oxidation process gives off energy. Okay, and you can see that this is energetically favorable by the way we've drawn these arrows, right? We've got a much longer forward-facing arrow. Okay. We know if we've got oxidation, we have to have something reduced, so the NAD is reduced. Okay, but net, we are giving off energy in this top one. So look at the arrow in this bottom picture. Wow, it is much more favorable in the reverse, but because we have that energy from that oxidation, that energy essentially provides the energy this phosphate needs to get over that energy hill and get added to this molecule. So we get over that energy barrier. All right, step 7, we are way over halfway. Look at what we've got. We've got our phosphoglycerate kinase. So kinase, moving phosphate from ATP to ADP, and that might look a little weird because when you come down here, you're going to say, well, wait a minute, it looks like I'm adding a phosphate to ADP instead of removing it from ATP. But remember, we've got a reversible reaction. So this particular enzyme can work in both directions. All right, when you look at this molecule, you may think, wow, that name sounds familiar. And if it does, it's because we looked at it when we looked at molecules that have that high, we'll just write it out again, phosphoryl transfer potential. There's a big driving force. They give off a lot of energy, okay, when they transfer that phosphate group. All right, so we are going to take this phosphate group and it's going to get added to the ADP. Okay, we're going to call this substrate, because these are both our substrates, substrate level phosphorylation. Okay, we're directly forming ATP in substrate level phosphorylation, directly forming ATP by transferring a phosphate from a high energy group or molecule, high energy, less stable, okay, to our ATP molecule. And remember that we have 2 of these molecules, so this whole thing would happen, so we would actually end up making 2 ATP in this step because it would happen twice. Okay, this is just the words of what I just said, just in case that is helpful later. And now we're going to look at steps 8, 9, and 10 all at once. So let's look at our enzyme names. Phosphoglycerate mutase. Ooh, I'm changing something, and look what I'm changing. I'm moving that phosphate from the end carbon to the middle carbon, okay, which is going to make the next reaction more likely. All right, we've got this enolase, and so this now is removing a water. So if we look, we have essentially you can think of it as we are removing this and this. They're bonding to make water and leaving, which means now we have this double bond between the carbons. Okay, so we have this enol form. This is not very stable. And so anyway, because it's not very stable, it is willing to give up this phosphate group. So it adds that phosphate group to our ATP molecule, or I'm sorry, to our ADP molecule. And we form ATP. Notice again, this is our pyruvate kinase. So as we're talking about putting phosphates on and off ATP, you can picture kinase. And then we have made it, and we are at our end point with pyruvate, this small molecule that we'll talk about more later, but it's considered the end of the glycolysis pathway. All right, once again, these are just words in case that is useful to you. Let's look at our overall reaction. And when we look at this, right, I'm starting with glucose. If you added up all those reactions, 2 individual phosphates, 2 ADPs, and 2 NAD+, all right, and our products are 2 pyruvate molecules, 2 ATP, 2 NADH, 2 protons, and 2 waters. If you go through, you will see that overall, we actually produced 4 ATP, but we used 2 at the beginning, and so net we made 2. If we look at the various reactions, so these are the 10 steps that we just did, okay, this summarizes them. You had summary slides in the last one that showed the structures. I really like those summary slides in the last video, but this one talks more specifically about each reaction. It tells you the enzymes, okay? Again, you don't have to memorize them, but you should have a feel for what each one does. Okay, it tells us what it does. And then this is interesting. So here is my standard Gibbs free energy change for the reaction. And here is delta G in cellular conditions. So remember, the standard would be with all the concentrations 1 molar, and at pH 7, that little prime symbol there. Cellular conditions, and y'all, it can make a big difference. Look at this. This one would give off 16.7 kilojoules per mole standard, but in cellular conditions, it gives off over 33 kilojoules per mole. This one would actually be endergonic under standard conditions, but is exergonic under cellular conditions. All right, so those cellular conditions can really make a big difference. All right, in our next video, we will start looking more at what happens to that pyruvate and a little more detail on some of the glycolysis.